we have all sorts of other examples of centripetal forces. For example, we have this contraption right here. In this contraption, we have a stopper on a string. We have the pink string. Now, if you'll notice, I've put a dot right here and a dot right here so I know when I can keep this string at a constant radius. Okay? And what we're going to do is we're going to actually analyze this. We're not going to talk about the numbers so much, but we're going to draw our free body diagram and summarize this and figure out what's going on in this particular case. Now notice, if I speed up, this goes up and the radius increases. If I slow down, the whole thing goes down. Okay? So in order to keep this balanced, there is a correct angular velocity to be at. If I go too fast, the radius increases. If I go too slowly, the radius decreases. So let's take a moment and look at the free body diagrams for what's going on here. So we have string, the stopper, and the mass hanging. Now, if we look at the forces acting on the mass hanging, there is a force of gravity acting down on the mass hanging. I'm going to put force of gravity with subscript of H for force of gravity acting on the mass hanging. There is a force of tension acting upward on the string. If we look at just the stopper, there is a force of tension acting inward on the stopper. It's the same string, so it's the same tension. And we have then a force of gravity acting on the stopper. Notice two different forces of gravity. Force of gravity acting on the mass hanging and the force of gravity acting on the stopper. If we sum the forces on just the mass hanging, that would be in the y direction, because that's just sitting there. It would be summing the forces in the y direction. Tension minus the force of gravity acting on the mass hanger is going to be equal to mass times the acceleration in the y direction. Class, what's the acceleration in the y direction of the mass hanging? 0. It's not moving up or down. We're trying to make sure we're in equilibrium, so the acceleration in the y direction is equal to 0. So we get tension minus the force of gravity of the hanger is equal to 0. So the tension equals the force of gravity of the mass hanging. In other words, the tension in the string is equal to the mass hanging times the acceleration due to gravity. I can adjust the tension in the string by adjusting the mass on the mass hanging. If I just sum the forces on this is going to be on the mass hanging. If I sum the forces in the in direction on just the stopper, I get tension, which is positive and it's in, is equal to mass times the centripetal acceleration. Now, what mass in that equation? When I sum the forces in the in direction on the stopper, it's equal to tension, which is equal to mass times the centripetal acceleration. That mass, Hedler, is what? That's the mass of the stopper. Because notice I'm summing the forces on the stopper itself. So this is the mass of the stopper. On the left-hand side, we have the mass hanging multiplied by the acceleration due to gravity. On the right-hand side, we have the mass of the stopper multiplied by r times the angular velocity. Now, all of this stuff on the right-hand side describes the stopper. Now, what I'm going to try to do is I'm going to try to have the mass times the stopper mass of the stopper times the radius stay constant. If I keep the radius constant, the mass of the stopper is constant as well. So notice what happens. If I'm spinning at a certain angular velocity, this is determined by the mass hanging, the radius, and the mass of the stopper. And if I increase the mass hanging, notice what happens to the angular velocity. Class, what happened to the angular velocity? It's increased, right? Which makes sense from the equation. If I increase the mass hanging, that increases the tension, that increases the angular velocity necessary to keep it moving or to keep the whole thing in equilibrium. Okay. So this is just another example of a situation where we have something moving in a circle. And in this particular case, what is the centripetal acceleration keeping the stopper moving in a circle? In this particular case, what's the centripetal force? Mrs. Song. It's okay, we'll have Wicket help you out. Wicket. What in this particular case is keeping this stopper moving in a circle? What's the centripetal force this time? Force of gravity acting on what?
On the stopper.
It's not the force of gravity acting on the stopper. That's okay. Gregor?
It's the force of gravity acting on the mass hanging.
Notice the net force in the indirection is the tension on the string, which we've shown is the same as the force of gravity acting on the mass hanging. So notice how the centripetal force can be caused by all sorts of different forces, and we'll clearly go through more examples in just a minute.